I have an interesting name, Jae Son. First name is Jae, last name is Son. This comes from my Korean name, Son Jae-sun. So I could be Jason Son, but I kept it short. What's even more interesting is the fact that in Korea, Son means the hand. And so it's very fitting that this webinar is about tactile sensing on human and robotic hands. So I did my PhD at Harvard giving robots the sense of touch. In order to do experiments, I had to actually develop tactile sensors, and that's how things started. And that was 30 years ago. So PPS was created after I finished, and one of the projects that we got funded was through DARPA, a government agency that wanted to capture what an experienced surgeon does so that they can use that information to develop surgical simulators. And you can see here a small sensor on a glove, and that was the beginning of tactile sensing projects. PPS is a small international company. I'm based in Los Angeles, and we have a R&D team in Glasgow, Scotland, and we have manufacturing teams in Seoul, as well as Vietnam, Ho Chi Minh City. And recently, we added an India team that handles our IT development. Over the years, we've worked with many large Fortune 500 companies doing various interesting projects, but most of them have been sort of more R&D and sort of limited application. And here's a short video about PPS.
There's nothing more powerful than the human touch. A touch can heal, stir emotion. A simple touch makes the world around us real. At PPS, we are unlocking the mysteries of touch to reveal what we could not before. Saving lives, improving performance, and making machines more intuitive. PPS is changing how we interact with the world by capturing the sense of touch.
Sorry about that. The video is a little bit laggy. And also, so the company started with basically tactile sensing technology. But since robots really didn't need tactile sensing years ago, we've found applications in medical devices. So here's one of the device that we developed called Nanoscan that measures pressures in your esophagus. By having 36 elements that's continuous, you see this sort of a picture image that's a lot more intuitive than these lines that the doctors have to really interpret. And nurses had to actually position the camera exactly at the same position, or otherwise you had to actually do the procedure again, which wasn't very pleasant because the catheter actually went through your nose down into your stomach. So, hold on 1 second. I'm gonna actually put okay. Um, uh, the product became market leader within several years because it was so easy to use, and it was acquired by a private equity company, and then currently it's being sold by Medtronic. Another device that we developed is called SureTouch. It's for breast cancer screening, and women love it because there's no radiation and there's no compression of the breast. And because it's such a novel technology, we had to get FDA clearance going through the de novo process, which was challenging. And recently we have clinically validated that combining SureTouch with ultrasound the efficacy of screening is much significantly better than mammograms. We won a number of awards, and the company is now rebranded as Bexa, and generating revenue should be
تعيد
profitable
بيكسا
this year
تعريف التجربة
and growing
بالكامل.
powerfully,
دقة بلا إشعاع،
including
سرعة بلا ألم، بفضل أحدث تقنيات الاستشعار.
So, shifting gears to some fundamentals. Um, People swap the term pressure and force, pressure being force divided by area, but there's another important difference between the two, which is that pressure is a scalar value and force is a vector. When I ask for your weight, people generally give a number, but they don't really think of it as being a vector towards the earth. And obviously, a vector can apply forces in different directions as well. Now, tactile is even more complex in that it gives a two-dimensional array of pressure or force arrays that really gives you insight into the contact mechanics between two objects, whether it's in your esophagus or breast tissue. Um, and people understand that when you go to a restaurant and you have a table that's wobbly, they've always experienced that. Even though the table's legs are made to be exactly the same length, and the floor is supposed to be also flat as well. But nothing's really perfect in this world. And so we, as engineers, even, we kind of forget that. Because if you look at this piece of weight, it's machined, very precise, and you would expect the bottom of it, which is flat, to give you uniform pressure. But you can see here, the pressure distribution is not uniform. You see that the mid portion is perhaps concave slightly, so it's not actually making contact. And you see this red spot here, which is maybe a piece of gunk or something that's stuck onto the bottom of the weight. Now that can be smoothed out by applying a compliant foam layer, as you see here. And robotics oftentimes use silicone skin to do the same sort of thing. So why is that important? Well, there's a story, children's story called Princess and the Pea, and this woman came to a castle and claimed that she was a princess, but she wasn't really had credentials or with any entourage. So the people tested her by seeing if she could actually feel a pea underneath a mattress, because only a real princess would have the sensitivity to determine something small like a pea under a mattress. And so sensitivity is very important. And this is where PPS capacitive sensing shines. Our technology uses the concept of capacitance, where two electrodes separate by a gap, but we actually have compliant material microstructures in between so that as pressure is being applied, the gap changes. And that gap change causes a capacitance change that we're able to measure and very sensitively. So here's a very simple single tact sensor, single element. So call it miniature force sensors, but you could also say it's also measuring pressure, contact pressures. But we can also take the same technology and turn it into array sensors, whether it's a single element that's laid out like Digitex, or creating an array out of rows and column, a grid, um, that gives you a much higher number of sensing elements. We also use various different sorts of material, from flex circuits to conductive cloth to stretchable conductive materials. That gives us a lot of flexibility and conforming to curved surfaces. And again, having electronics near the sensor, we have amplified the performance of the sensor accordingly. And by changing the dielectric material between the two electrodes, we can custom tailor the sensor for very sensitive applications where sub 1 psi, to industrial applications where we need hundreds or thousands of psi So it's very versatile or flexible. And this is a example of a test report that we provide with each system that we ship. And so after we calibrate, we want to verify that it's giving us the ideal result, which is shown here in red line here. So if we apply 5 psi, we'd expect to get 5 psi. And each element is calibrated. And so what you see here looks like a single line, but this actually can be over 3,000 lines because one sensor can have over 1,000 elements, and we repeat this 3 times. So you can see that it's very consistent in terms of the sensor response, and the signal to noise ratio of exceeding 2,000 to 1 is pretty common. Now, compared to resistive sensor technology, capacitive shines in terms of sensitivity and repeatability. However, resistive sensors are much faster because the electronics required to measure resistance is much simpler than capacitance measurement. Now, in robotics, there's several other sensor technologies that has been developed. Um, our sensor being less than 1 millimeter and being able to curve multi-curved surfaces can be applied to robot fingertips or other curved surfaces. Gel site or camera-based sensors use MEMS-based camera to give you high resolution, but there's a soft compliant layer that is needed to make the tactile sensing work. Well, that soft compliant layer, as I demonstrated before, distributes the pressure. So even if you had a very high fidelity or high resolution contact mechanics, the silicone material or the compliant material would distribute it. So having high resolution doesn't really buy you that much. And also, because of the form factor, it's a bit more bulky and difficult to integrate. Some companies have used MEMS technology to measure force, and oftentimes in 3 axes to get shear information. However, when the force sensors are embedded in silicone, some precision is lost, and the MEMS sensor can easily be damaged, which is a problem that our sensors don't have. Our sensors can take overloads without really getting damaged or broken. It does take some time to recover if the forces are very high or held for a very long time, but it recovers just um, without any damage, which is good. Now, going back to the Tactile Glove project, what resulted from that is a very simple sensor. You see this gray region by the thumb? That's a formed sensor that measures the contact pressures and analog voltage out. So that was evolved into finger TPS, which allows you to have up to 6 sensors. And by using lycra spandex conductive material, very thin, conforms to each finger. And so researchers like it because it's very minimal, and you can do very dexterous or sort of delicate tasks. And we also provide a force sensor, so each person wearing the sensor can calibrate it so they know exactly what they're measuring. However, it's a bit cumbersome to use as a research, it's really a research tool. And so we went further to develop the tactile glove. And this actually opens up an interesting question because people often talk about grasp force, and grasp force is measured using a hand dynamometer as shown here. But if you actually understand the contact mechanics between the hand, the fingers, and this device, it's actually lots of different directions that it's pointed and much more uh, complex or matrix of information than just single number that this device provides. So tactile grasp gives you insights about what's happening. as is this demo of crushing a soda can. You can see how the pressures distribute over the whole hand. The sensor has 65 elements and it samples at 100 hertz using Bluetooth 5. And it has a pretty high dynamic range of being able to measure up to 80 psi, which is very high, to detecting very low pressures or forces down to 3 rams. The majority of the application for the tactile glove has been in the ergonomics field, understanding worker injury, how much effort is required, and also in product development, whether it's tools or wearable devices. Um, having this pressure contact information helps you improve the ergonomics. We're continuing to improve and evolve, where the tactile glove combined with accelerometers on the back side gives you hand pose information so that you can actually do things like this, where you can actually measure the grasp pressure as well as the hand position here. Now, this is very interesting to AI robotics because now we're able to actually capture the contact pressure or tactile data from the hand during manipulation so that that information could be used to train robots to do similar dexterous manipulations that humans that we do, so that robots can do very challenging tasks such as picking up delicate fruit like strawberries. And similar to how vision has evolved into using AI and neural networks to enable robots to identify and go and grasp objects. Well, similar type of model would be used for tactile data, where it can be the data collected can be fed into a AI transformer that can enable or teach robots to grasp objects much better than we're able to do today. So when you don't have vision, tactile becomes much more important. We do this type of task of grabbing something from our back all the time, and we don't really think too much because we can actually feel what we're grasping. Now, some tasks where you can see what's happening, but there's really not much of visual cue to what's going on. But if you look at the bottom traces here, you can see that the peak pressure gradually decreases in order to have a smooth shuffling experience. And some people maybe even have difficulty in this. And so it's interesting to see the contact pressures for these sort of tasks. So now I'm going to shift over to doing a little demo. So give me 1 second here. Um, let me see. Okay. So you can see pressure and force. The red trace is the force, and the black trace is the pressure here. And I'm going to do a very simple task. I'm going to lift up this bottle of water. Okay, I'm going to do it a few times. And you can see the total force at the pressure that's used or required to actually lift this. But what happens if I actually grasp a bottle that's full? Without really thinking, we just instinctively grasp harder because otherwise we would actually drop the water bottle. So we've done this because we you have a lot of experience doing these simple tasks. And also you can see that if I just use two fingers to grasp this object, then you can see that well, I'm grasping harder here, so I don't drop it, but you can see that the pressure is higher, but the force remains roughly the same. So, but I mean, I could also grasp much higher than needed, but generally we're kind of conditioned or programmed to minimize the amount of effort that we use. So, so I'm gonna go into some fundamentals of just that simple task. Okay. First thing is that, when you're actually trying to grasp an object, you need to determine when you actually make contact. Now, you could do that using many different methods, including motor torque or force sensors, but using stress rate sensors at the surface of the contact gives you a much higher fidelity signal than force sensors, as well as avoiding accelerational false signal due to acceleration. Oftentimes, when you see a demo and you see a robot grasping an object, the object tends to move because it doesn't have tactile sensing or it's not able to determine that it made contact. So what we can do is actually, this is a project we did with Greg Hager at Yale, where he was developing this stereo vision system to guide robots, this Zero robot. And I added tactile sensors onto this gripper. And you can see the curvature on this here, which is very important, and I'll explain next. So vision is used to actually guide the robot to grasp an object. Okay, once near there, it starts closing, but we actually see that the contact occurs at a location which is not very stable. And so rather than continue to close the grasp and move the object or, maybe have the object fall, we actually change the position of the gripper so that the contact point is more central, which is only possible when there's curvature on the sensor. And then we close the other grip side of the gripper by actually moving the robot and closing the other arm to get symmetrical contact, and then we increase the grasp force. Once the object is grasped, we're pretty good at holding it without dropping things. And the way that works is that here is a force, grasp force, and the second column is the weight of the object. So we grab the object, lift it up, and then by slightly reducing the grasp force, we actually detect a vibration that occurs before the object actually slips. So that information can be used to say, hey, better increase your grasp force if you don't want to drop the object. So you're able to determine grasp slip before it actually happens. Now, there's lots of humanoid robot hands that's been developed recently, which is a very complicated endeavor. And because of that, majority of the robot hands actually don't have tactile sensors. And so this is an unsolved layer in robotics. There's really no standard in tactile sensing integration. There's no common data model or developed ecosystem, which is why we developed the Robotac to bridge that gap. Vision, only robotics has challenges when there's occlusion, or if the object has compliance, such as a strawberry, or there's no slip signal so that the object can be dropped. And so over the years, we've done a number of interesting projects in robotics. We provided the tactile sensor for the Barrett hand, which is Bill Townsend's company. And he was actually the first grad student for Ken Salisbury. And Ken was also my advisor as well. We also provided a gripper sensor or tactile sensor for the PR2 robot for Willow Garage, who developed the ROS robot operating system. This Toyota 21, I think, is still probably the most advanced use of tactile sensing and manipulation, as this video demonstrates. So everything behind the red has tactile sensors, and being able to pick up a straw like this and do this sort of manipulation would really not be possible without tactile sensing that gives you the contact location as well as the forces that you're grasping the object. Now, Robotac not only provide the grasp force, but also it has an accelerometer to give you vibration information. And all of this is over the ROS operating system. The sensor can be customized to different robot fingertips or palms or other parts of the robot hand. And it has 12 elements per sensor. So rather than providing tactile data, we want to provide something that's more useful for manipulation. So taking the tactile data, we want to provide initial contact that's very sensitive. We want to provide where the contact is happening so that the grasp can be stable. Obviously, force magnitude and contact area are important information to know in order to do manipulation. Slip detection, pressure distribution for shape identification, or vibration for material textures are also other useful information that can be provided to the robot control higher level people over the ROS2 interface. So we're trying to make tactile sensors much easier to use so that companies that's doing humanoid training with for robots can do this more easily. Other companies are developing robots for industrial application to do difficult work for humans, such as Boston Dynamic. And obviously, Amazon is very interested in pick and place and type of function, and they've implemented. And LG Electronics at the CES January this year demonstrated their robot that will help you do chores in the home. So a lot of different applications. And also a lot of different ecosystem of robot OEMs, AI researchers, system integrators, university, and application developers. So Robotac serves to provide solution for that ecosystem, similar to how the Raspberry Pi makes embedded computing much easier. So not only the tactile sensor, but the Robotac platform with APIs and ROS operating system, so that the robotic developers can focus on higher level tasks. So, so that's it. Thank you for listening. And let me see. I think there's some questions here. How much slow are capacitive sensors than resistive? How fast can capacitive sense be read out in hertz? Yeah, so the common frequency is about 100 hertz. However, if you have thousands of elements, we're not able to provide that sort of sample rate. So the tactile glove has 65 and it operates at 100 hertz. So I think that's plenty fast for most applications. However, we don't recommend using our sensors for like impact detection, where you need kilohertz of sampling rate. Any other questions? What is the minimum pitch of the capacitor sensors in the array? So we've made sensors that are 1.5 millimeter by 1.5 millimeter, and also by if you need higher resolution, such as maybe nip roller application, we've done like 0.5 millimeter by 4 millimeter type of configuration as well. Um, what do you think of screen printing to make capacitive touch sensing? And there are better technologies? What do you think of screen printing to make capacitive touch sensing? Um, yeah, no, we're very interested in that. I've attended these printable electronics conferences and been following them. It's very cool, but unfortunately, they're not quite there for prime time because the flex circuit industry is not just about the traces, but the vias and all sorts of other constraints to that you have to follow to make a reliable uh, flex circuit. And um, so I think it's great to see stretchable electronics that we've actually doing some work with collaboration with, but the whole ecosystem of creating reliable sensor using that type of technology, I don't think is quite there yet, but it's progressing very nicely. So thank you for the presentation. We are another team developing an anthropomorphic hand. How is the precision of capacitive sensors affected when the fingers are close to sources of radiation in standard commercial environments? Yeah, so actually, our sensors are shielded, um, but we really haven't had too much issues with noise. Um, Having said that, we've probably had more issues with Bluetooth signal connections in factory environments with high ceilings. And so, but with respect to noise, we haven't really seen too much of a issue. Would it be possible to get a budgetary price for basic tactile sensor for 5-finger robot hand? Um, sure. I think it might be good for us to see what sort of the finger it is, but we actually provide the development kit for Robotag starting at $5,000. Is it possible to share the slide? Yes. So um, everybody that's registered will be getting the presentation um, summaries, and we can also share the slides as well if you like. So what kind of electronics do you use? Sorry. What kind of electronics do you use to detect capacitors? Are you using off-the-shelf ICs, CDCs, or custom designed ones? The answer is actually both. We've tried pretty much everything. We also developed our own capacitance sensing electronics. Um, we use also a sort of a not commercially available, but we have access to a unique IC that has very good performance. Um, and so we're kind of agnostic to the electronics. Sometimes if you have very large capacitating elements, you have to use a particular IC, whereas others are more higher fidelity for smaller capacitance measurements. What is the maximum low capacity of tactile sensors? As I showed before, we've done things that are thousands of PSI, meaning in very industrial high pressures. I believe robotics doesn't really require that. In fact, initially when we developed the Robotax, we thought maybe 45 PSI would be um, good, safe measure. But then we realized that's probably too high because most robots can't generate that much force. And so we lowered that down to 15 PSI. But for robots such as like the Atlas, the Boston Dynamics, that want to do heavy industrial type of work, they'll need higher pressures or force capabilities. And so we do customize the sensor design for the application. What do you find the most common problem that are encountered when integrating capacitive tactile sensors? What is the most common failure mode? Very good question. I think the most challenging thing is just actually simple electrical connections. When you're dealing with thousands of sensors or hundreds of connections, any one of them can cause, a failure. So you really have to be very reliable in terms of how you build a sensor. And so similar to semiconductors in some sense. And the taxol density is really limited by the capacitance value. We're measuring capacitance in the femtofarads, very small amount of capacitance when you get down to 1.5 millimeter. And the gap between the electrodes is about 200 microns. So, and to do that very fast requires, you know, a fair bit of know-how or experience. Ah, accelerometers. You know, in our hands, we actually have four different types of mechanical receptors. Sensors that can detect stretch, sensors that can detect vibration, sensors that can detect local deformations. And so vibration is actually, I think, a very useful addition to tactile sensing for things like determining contact or um, feeling the surface texture of different materials. And so we included that. And so, we haven't used it that extensively, but there's been applications where that can be very useful. One of which is in automotive, where mating connectors, that snap feeling can be well detected very nicely with accelerometers. Okay, I would like to use tactile sensor to accelerate robot hand manipulation for learning dexterous tasks. What is the minimum resolution you think you needed, like pictures or array density for sensor, sensor elements? Good question. It depends on sort of the size of the hand as well, but if you think about humanoid hands, like the five-finger Tesla hand, I think we've gone with about 3 millimeter resolution because having higher resolution doesn't really buy you that much because let's say if you have 2 millimeter or 3 millimeter thick skin, then even if you apply a sharp pointed um, pencil type of contact, that sharp point gets distributed. And so having higher resolution doesn't really buy you that much, as I talked about with camera-based sensors that have high resolution. So, but I think also resolution does depend upon the type of task you're going to do. If you're going to do generic manipulation tasks, I think 3, 4 millimeter is actually pretty sufficient because you can actually centroid the contact location to about 1/10 or even 1/20th of the spatial pitch. So if you have a 10 millimeter sensor, then you can centroid that down to less than 1 or 0.5 millimeters. So, there's uh, everybody wants higher resolution or thinking that's best, but sometimes that's not quite necessary. Uh, that's the question. This is great. Is there any specific shielding method used? Um, there's, I guess, different types of shielding materials that we can use, from conductive cloth to flex circuit type materials that we call industrial tactile sensor. And that one, because of the stiffness, doesn't conform. But for industrial application where you just need a flat sensor, that's fine. And that allows you to have sensors that are down to like 0.3 millimeters thick. Do you ever use touchscreen controller ICs or large arrays? For large arrays. In some ways we are, but generally the touchscreen ICs are not designed for high dynamic range. So the amount of pressure level that you can detect is not really optimized for tactile sensing because they're just detecting, single touch, right? And so the best sort of CDC for tactile sensing is a bit I don't know, scarce, and you have to kind of choose the right IC for the application. Wow. Well, share the notes by the note taker. Yeah, yeah. So everybody should get a meeting summary. Um, for the Tesla team, the demos you're showing are those using purely the capacitive tactile sensors, or do they include the six-axis sensor at the fingertip you were showing? Do you find that you were missing shear information? Dr. Ryu, you want to answer that? Some of the videos, were they using, tactile sensing in the videos, or um, have you used force, shear forces and the force torque sensing?
Uh, the the most demo is we just use just the joint current feedback, but the one demo is the connector assemble demo. We used some keep the 6-axis FT sensor, yeah, data, yeah.
Okay, great. Well, an hour's time is up, so thank you very much for attending, and yeah, we'll be sending you these meetings. You should be getting that. Please contact me if you don't, and we'd be happy to share more. So thank you again. Appreciate it.